Hello everyone, I am Jahek. In this video, I'm going to show you and explain what is the gravitational lensing. The gravitational lensing is the deflection of light by a massive object, creating a phenomenon like multiple images, luminous arcs, or a ring-like image of the source. And next, the objective in this video is to explain the basic mechanisms of gravitational lensing, and we also discuss the applications of different gravitational lensing in astrophysics and also cosmology. So let's see the animation of gravitational lensing. We have a light source and massive object at the center. So the light source is emitting the light rays. We got an observer on the left side. So the light ray coming from the light source is bent by massive objects. And by extrapolating the light ray, we get two image 1 and 2, that are on the opposite side of light source. So for the special case of Einstein ring, the light source lies behind exactly the massive object. So the image 1 and image 2 are now being formed symmetrically about the axis connecting the light source and the massive objects. Firstly, we have a look at geometry and lens equation. So we know with the completion of general relativity, Einstein gave the equation for the deflection of light as shown in equation 1. And from basic geometry, we have equation 2. And also in the astronomical sense, the angle theta is extremely small so that we can apply the approximation to the distance between the image 1 to the source. And then we can get the equation 3. So after rearranging it and substituting it into equation 2, eventually we know the relation between beta and theta as shown in equation 5. So this equation tells us that the relation between actual angular position of source and the observed angular position of the image 1 of the source. And that is called the lens equation. And secondly, so in a special case where the source lies exactly behind the lens, the beta equals 0. So we solve equation 6 for theta, and the angular radius theta is called Einstein radius theta subscript e, as shown in equation 7. So besides that, to quantitatively analyze the lens image of the source, we define the magnification mu as the ratio between the solid angles of the image and the source, as shown in equation 8. By solving the lens equation, the magnification mu becomes equation 9, where the mu plus minus represents the magnifications of the first and the second images of the source. And then now let's have a look at the different types of gravitational lensing. So we have three types of gravitational lensing here. So firstly, we have the strong lensing. The examples are multiply image objects, the Einstein rings, the giant luminous arcs, and arc floods. So the applications of strong lensings are to determine the amount of dark matter and the value of Hubble constant, and also to determine the separation of quasars and their redshift distribution. So this is an example of strong gravitational lensing. And next, the second type of gravitational lensing is microlensing. Its applications are to observe the fluctuation of brightness of the large Magellanic stars to study the dark matter candidate that are brown dwarfs. And secondly, we use microlensing to observe the light curve of quasars caused by compact objects. Here is an example of observations of microlensing light curve. Thirdly, we have the weak lensing. It can only be measured statistically because the effects on every single object are too weak. For the application of weak lensing, we can apply Fourier analysis on the lens image, and eventually we deduce the mass distribution of the foreground cluster. As a conclusion, the gravitational lensing is a powerful tool for understanding the universe. It allows us to study the distribution of matter and distant galaxies and refine the cosmological models. And thank you for your watching.